Hello, this is my work energy reassessment, and I want to solve this problem using different fundamental principles. So you throw a ball straight up on the moon to a height of 20 meters. What was the ball's initial velocity? To solve this, you first need to pick a system, and I wanted my system to be the ball plus the moon. That way there are no external forces acting on the system. And the work of the system is the change in kinetic energy of the ball plus the change in potential energy of the ball plus the change in kinetic energy of the moon plus the change in potential energy of the moon. And the kinetic energy and potential energy of the moon do not change with respect to the ball. So the work done on the system is 0. The final kinetic energy is 1/2 mvf squared, which the final velocity is 0 because at the peak at the 20 meter height that it reaches, the velocity is 0. And 1/2 mv I squared, and that's the initial kinetic energy which you're solving for, the VI term, and the plus the mass of the ball times the gravitational constant of the moon times the height that the ball reaches, y2, minus the mass of the ball times the gravitational constant of the moon times the initial height, which we are setting to be 0, so that term becomes 0 as well. So then we solve for VI, and we get 2 times 1.625, which is the gravitational constant of the moon, times 20 meters, which is how high it goes, and we get that the initial velocity is 8.06 meters per second. Next, we want to find out how long it took to get to 20 meters. So we know that change in momentum is, well, first, the reason why we want to use momentum is because we use work energy here, and there's only 2 fundamental principles that are applicable, and we use the first one here, so we need to use the second one here. And so the change in momentum is equal to the mass times the change in velocity, which the net force times the delta t, or impulse, equals mass times the change in velocity. So F net is m times the gravitational constant of the moon. So we want to solve for delta t, and the masses cancel just like they canceled up here. So we plugged in that 8.06 that we got from this previous answer, which is the only way we would be able to do it using the momentum principle. So then we know that the change in velocity over the gravitational constant, so we solve that and we get 4.96 seconds is how long it's in the air.